Okay, good morning, everyone. So we're going to start our lecture. So this is going to be our actual final lecture on randomized algorithms. Right, and so today we're going to look at an interesting randomized algorithm for solving linear programming. Okay, so this algorithm is by Savage, or sorry, not Savage, Seidel. Okay, so this is Seidel's linear programming algorithm. Right, so first of all, linear programming, so what we talked about is that linear programming is actually a very general methodology for optimizing a linear objective function subject to linear constraints. Okay? And so it turns out that many problems you can model using linear programming. So for example, we talked about this example where, let's say you have a farmer, right? And he wants to plant some stuff and make some money. So he's going to plant wheat and barley, okay? And however, when he decides how much wheat and barley to plant, he's subject to a lot of constraints, okay? So first of all, let's say that this farmer only has 100 acres of land, okay? So then if he plants W acres of wheat and B acres of barley, then W plus B has to be less than 100, right? Because he's only got 100 acres of land. Okay, and there can be other constraints. So for example, for each acre of wheat, he might have to use 3 kilograms of fertilizer. And for each acre of barley that he plants, he has to, let's say, use 5 kilograms of fertilizer. Okay, and so suppose this farmer only has 420 kilograms of fertilizer. So in that case, we have another linear constraint, right, which is over here. Right? So if you're going to plant W acres of wheat and B acres of barley, then you have to satisfy this fertilizer constraint. And there can be additional constraints. So for example, maybe he needs to use pesticide also to plant stuff. Okay, and let's say he needs to use 2 kilos of pesticide for each acre of wheat and then 1 kilo of pesticide for each acre of barley. And let's say that he only has 160 kilograms of pesticide. Okay, all right, so that forms another constraint. And you could have more and more constraints, okay? But in this problem, we're going to have 3 constraints on how much wheat and barley the farmer can plant, okay? So you see that all of our constraints are linear constraints, right? And now, let's say the farmer is also trying to maximize some sort of linear objective function, okay? So let's say that he makes $3 for each acre of wheat he plants and then $4 for each acre of barley that he plants. So then he wants to maximize this function 3w plus 4b subject to these constraints that he has to satisfy. Okay, so that is this is an example of a linear programming problem. All right, so in order to solve problems like this, it's very useful to visualize these constraints and the objective function. Okay, because that provides us a lot of intuition for how to design a linear programming algorithm. Okay, so let's try to visualize all of these constraints. Okay, so the first constraint is the land constraint. Okay, so we have 2 variables here, W and B. So when we visualize this, we can just do it in 2D. Okay, so we're going to draw this constraint in 2D. And so let's say that the y-axis here is going to represent the amount of wheat that you plant, and the x-axis is going to be the amount of barley. Okay, and we need that W plus B is at most 100. Okay, so when you visualize this, or when you draw this in the plane, right, that corresponds to this region, this triangular region that's shown in blue. Okay. In other words, any point which is in this blue triangular region is going to satisfy this constraint, right? And any point which is outside the blue region is not going to satisfy the constraint. Right? So therefore, we can only consider points which lie in the blue region. Okay, so that's the first constraint. And now let's look at the second constraint. Okay, so the second one is we have this other linear inequality over here. Right? So if you draw this in the 2D plane, then you're going to get a figure which looks like this. Okay, so this figure should actually extend beyond the top over here. Okay, so it's actually it forms a triangle like this. Okay, but it's being cut off based on my range. Right, and so here in the second constraint, what we're saying is that all of the acceptable or feasible W and B pairs they all have to lie within this pink region over here. Okay, all the values in the pink region satisfy the second inequality, whereas anything outside the pink region violates the pink inequality, the second inequality. Okay. All right, and now since you need to satisfy both the first and second constraints, then what we need to do is to take these two regions and look for the points which are in both of these regions. Okay, so therefore we need to intersect these two regions. You need to take the blue region and the pink region and intersect them. Okay, and when you intersect them, what you're going to get is you're going to get this shape over here. Okay, yeah. So you see that some of the points which were previously in the pink region are now no longer feasible. Okay, so these points which are in the intersection, we're going to say that they're feasible. And you can see that some of the previously pink points are no longer feasible because they don't satisfy the land constraint, right? They're not in the blue region. Okay, and likewise, you have some points in the blue region which do not satisfy the pink constraint, and so they're also not feasible. Okay, so when you intersect the blue and the pink regions, you're going to get this little shape that we have over here. Okay, so that is for the first two constraints. But oh right, and when you intersect them, yeah, you're going to get this this thing over here. Okay, and we need to add one final constraint, which is the third pesticide constraint. Okay, so the pesticide constraint, if you just draw it by itself, so again, you're going to get some sort of triangular region, okay, which is being cut off. And so since you have to satisfy all three constraints, okay, then what we need to do is to take the region corresponding to the first two constraints and intersect it with the pesticide constraint region. Okay, so you need to take these two shapes, what do you call this? The purple shape, I guess, or the blue shape and the green shape, and then intersect them. And when you do that, you're going to end up with this, this yellow shape over here. Okay, so this yellow region are all of the WB points, right? So here you have W and here you have B, right? So this yellow region is the set of all WB points, which satisfy all three constraints. Okay. And the linear programming problem is to maximize this function, 3w plus 4b, while only considering points in this yellow region, which are the only feasible points for this LP. Okay, so that's the problem that we're trying to solve. Okay, now, so now we're going to look at how do we maximize this linear constraint, this 3w plus 4b, within this yellow region. Okay. All right. So what we're going to do is we're going to draw the level sets of this function. Okay. And what I mean by level set is that we're going to draw a line. Well, we're going to draw some sort of curve. The curve is going to turn out to be a line. Okay. But in general, it's going to be a curve such that on this curve, this function 3w plus 4b is always going to have the same value. Okay, so that's a level set of this 3w plus 4b function. Okay, and now because this 3w plus 4b is actually a linear function, then the level set is actually going to be a straight line. Okay, in general, it could be a curve, but because we have linear functions, it's going to be a straight line. Okay, all right, so this is what I'm showing over here. Okay, are these various level sets. And now I need to say something, which is I made a mistake when I drew these lines. Okay, so I'm sorry about that. So these lines that I'm actually drawing here are actually incorrect. Okay, because I was supposed to draw like 3w plus 4b, right? So for some reason I somehow drew 3b plus 4w. Okay, so all of these things are actually the level sets for 3b plus 4w. Okay, so I'm sorry about that. So anywhere you see like 3w plus 4b, just sort of in your mind, just switch that over to 3b plus 4w, okay? But qualitatively, what I'm saying, okay, so the basic idea that I'm trying to express is still correct, okay? But I'm sorry that I drew the incorrect picture. I just noticed this, you know, like this morning, so I didn't have time to fix it, okay? So yeah, sorry about that. Okay, but anyways, what we're trying to do is to consider the level sets of some sort of linear function. Okay, which is supposed to be this 3w plus 4b, but again, I drew the wrong thing. Okay, all right. But anyways, if you look at these lines, right? So imagine that this is actually 3 3b plus 4w, okay? And actually this value, these values are all also incorrect, okay? So I made a bunch of mistakes. I don't know why I made so many mistakes on this figure. But anyways, so just you can kind of see that every point on this red line over here, okay, they're all going to have the same value for 3b plus 4w, right? Like if you take this point, right, this is like 30, right? So this is going to yeah. So this is the w-axis over here, and this is the b-axis. Okay, this is the b-axis. Okay, so if you take this point, then the value here is actually 120. Right? If you take this point, okay, and if you take this point, it's also 120. Hey, wait a minute. What is this? Yeah, right. Yeah, right. So yeah. Okay. Anyways, yeah. So if you look at all the points on this line, okay, they all satisfy 3b plus 4w equals 120. Okay, now if you take the second line over here, right, then all of them are going to satisfy, what is this, 3b plus 4w equals, what do we have here, 200, okay, right, and so on, okay. So all of these lines are going to satisfy, you know, when you plug in this 3b plus 4w equation, they're going to have the same value along the entire line, okay. Yeah. Now, so suppose that we're actually trying to optimize this function, 3b plus 4w, okay? Then what you see is that as you move these lines sort of upwards and to the right, then the values that you're getting are getting larger and larger, okay? So for example, here, what do we have? So 3b plus 4w, wait, so this is, geez, I should have done this differently. This is 3b plus 4w is 200. Okay, so this is 3b plus 4w is what is this, 70? Okay, so this is going to be 280 here, and then this is 3b plus 4w is 360 here. Okay. All right. Yeah. So, anyways, what you see is that as you move, you know, in this upwards and rightwards direction. Okay, the values that you're getting for this objective function, which is 3b plus 4w, okay, 3b plus 4w, the values that you're getting are actually increasing, okay? And so what that means is, since we're trying to find the maximum possible value for 3b plus 4w, okay, then what you want to do is, within this feasible region, you want to move as far as possible in this upwards, rightwards direction. Okay, and when you move as far as possible, however, you need to stay within the yellow region. Okay, because for example, if you take this line, okay, well, this is going to have a very large value for 3b plus 4w. Okay, it might be, let's say you get like 600 here. Okay, however, all of the points on this line, right, all of them are not feasible because they're not within this yellow region. Okay. Whereas if you take you know, if you take this line, okay, then all the points in here are feasible, right? But you're not maximizing this function 3b plus 4w, because here, if you switch to this other function, right, you also have points which are feasible in this other line, and they have a larger objective value. Okay, and in fact, you can push this even farther. You can push this to this line over here, and here this line still has at least one point which is feasible, which is namely this point over here. Okay, this is still a feasible point, and this gets you an even larger objective value. Okay, so basically, yeah, if you push these lines as far as possible while still touching the yellow region, okay, then you're going to find that this point, okay, w equals 40 and b equals 60. Sorry, so I switched the axis here. Okay, so I'm sorry about this. Yeah, so this should be like b here and then w. Okay. Anyways, yeah. So this point, okay, b equals 40 and then w equals 60. Okay, this is going to be the farthest that you can push these level sets and still be feasible. Okay, because this point is still feasible because it still intersects the yellow feasible region. Okay, and furthermore, this point maximizes your revenue because you've gone as far as possible in this direction. Okay, if you go any farther in that direction, then you can increase your revenue, but you will no longer be feasible. Okay, yeah, so that's basically the approach that we're going to take to solving these linear programs, is to try to find a line which is just barely touching the feasible region, okay, which touches the feasible region at possibly just one point over here. Okay, and then we want to move these level sets as far as possible in this direction, which is perpendicular to these level sets. Okay, you see that the directions that we're moving these level sets, right? So if you move perpendicular to the level sets, then you're going to increase the objective function more and more. Okay, any questions about this? Okay, yeah, so just to summarize everything, so the feasible region is the area where all of the constraints are satisfied, okay? And then we're trying to take this objective function, so you draw a level set for this objective function, and you want to push it in a perpendicular direction as far as possible until you just until you're just about to leave the feasible region, okay? And so when you see that, as you push this line, so the point where you're just about to leave the feasible region, okay, then you're going to intersect the feasible region at just a single point over here, this blue point over here, right? And so the optimum, value is going to lie exactly at this blue point over here, okay? And this blue point is so we're going to call this an extreme point. So where does this blue point come from? Well, you notice that this blue point is formed by the intersection of some of these constraints, right? So actually, let me switch to a different color over here. Okay, so, right, so this blue point comes from the intersection of two of these constraints, okay? So which were these constraints? So I think this one was the land constraint, and this other one is what, the fertilizer constraint or something, right? Okay, anyways, so because remember each of these constraints basically creates a straight line, right? And then so the boundary of this feasible region comes from the intersections of these lines, okay? And in this case, the optimum, which is at this intersection over here, this comes from the intersection of the land constraint and the fertilizer constraint. Yeah, so so the optimum lies, and the reason so you notice that this point is exactly at the intersection of two constraints, right? And this is because we're working in two dimensions. Okay, so when you work in two dimensions, right, then two lines are going to intersect at a unique point. Okay, unless the lines are parallel. So in general, we're not going to consider those situations where these constraints form parallel lines. Okay, we're going to assume that all of the constraints are not parallel to each other. In which case, because we're in two dimensions, then two lines are going to intersect at a point. And so that means that the optimum always lies at the intersection of two constraints. And we're going to call these constraints the basis of the optimum. Okay, right, so let me go back to red over here. Yeah, so these are the basis for the optimum. All right. Now, it is possible in two dimensions that you have three or more constraints which let's say intersect at a point. Okay, so this is a possibility, but it's but in general, when you consider like kind of a random instance of linear programming, okay, or when you consider just there's a very low probability that you have three lines that actually intersect at a point. Okay? So in general, we're just going to assume that for the LPs that we're going to deal with, we don't have this special corner case situation where you have three or more constraints intersecting at a point. Okay, we're always going to assume the constraints, only two of them intersect at any point. Okay. Yeah, so this is called a general position assumption. Okay, all right, so that's the problem that we're trying to do. Okay, so we have these linear constraints which forms this feasible region. And then we have a linear objective function, and we're trying to find what is the value which optimizes this linear objective function. Okay, so now we're going to give a randomized algorithm for solving this. Okay, and the main observation for this, so we're first of all going to talk about two-dimensional LPs, right? So currently we have two dimensions because we have the wheat and the barley. Okay, so in general, you can talk about LPs in higher dimensions, but we're going to start off by talking about the 2D case, and that's going to give us a lot of intuition. And we can extend that intuition over into the higher dimensional case. Okay, so let's start with the 2D LPs. Okay, so the key observation is that in 2 dimensions, because the optimum is defined by 2 constraints, right? Then you could have many constraints. You could have like 100 constraints. Okay, but the optimum is still going to be defined by 2 constraints. Okay, just like over here, right? The optimum was defined by the land and the fertilizer constraints, even though we had 3 constraints. Okay, and even if you have 100 constraints, the optimum is still going to be determined by just 2 of these constraints. Okay, then that means that all of the other constraints are useless. Okay, they're redundant, meaning that you can remove them, you can remove the redundant constraints and not change anything. Okay, so what I mean by that is, all right, so suppose you have this situation over here, okay? So here I'm drawing a bunch of constraints. So each of these lines is representing a constraint, okay? And the purple line is saying that, all of the feasible points have to lie on the purple side, okay? So for example, for this constraint, right, we're saying that all of the feasible points have to lie below this line over here, okay? And for this line over here, we're saying that all of the points have to lie above this line over here. Okay, so I'm drawing a bunch of these constraints, and suppose that the objective function. So remember that when you try to optimize an objective, it corresponds to moving in a particular direction as far as possible, right? So let's say that we're trying to move in this direction as far as possible. Okay. Then in this case, the optimum value is going to lie at this star over here, right? Because basically you need to satisfy all of these constraints. So for example, you need to stay within this triangle, okay? And within this triangle, you're trying to move up as much as possible. And so the farthest you can go is to the star point. Okay. Right. Now, in total here, we have, we have 1, 2, 3, 4, 5, 6 constraints, right? 5 constraints, okay? But you see that this optimum is lying at the intersection of 2 of these constraints, okay? And so these 2 constraints where the optimum lies, okay? We're going to say that they're tight constraints, okay? Whereas all of the other constraints where the optimum does not lie on those other constraints, we're going to say that those are redundant constraints. Okay, so for example, this star here, right, it doesn't lie on this constraint, this constraining line over here, okay? And so we're going to say that this is a redundant constraint, and likewise, these 2 other ones are redundant. Okay? And so what I mean by redundant is that suppose you actually removed this constraint, okay? Then would the optimum point change? Well, the optimum point would not change, even if you took out that constraint. Okay, even if you took out the constraint, the optimum would still lie at the star right here. Okay, likewise, suppose you took out this redundant constraint. Okay, would that change the optimum? No, it would not change the optimum. Okay, the optimum would still be at the star. Okay, and if you took out this constraint, right, you can take out all of these redundant constraints at the same time, and that would not change your optimum. Okay, and so that's why they're redundant, because you can take them out and you don't change the problem, actually. Okay. Now, on the other hand, these tight constraints, okay, these, if you remove a tight constraint, then it is going to change your optimum. Okay, so for example, suppose you take out this tight constraint. Okay, so suppose you just sort of remove this constraint. Okay, then the optimum would actually switch, would change location. Okay, it would change to over here, right? Okay, so so if you take out and if you take out the other tight constraint, right? If you take out this one, right, then the optimum would move over here. Okay, so the difference between the tight and the redundant constraint is that for the redundant constraint, if you take it out, you don't change the optimum. Whereas for the tight constraints, if you take them out, you are going to change the optimum. Okay, any questions about that? That's like the key point for this algorithm. Okay, so any questions about this? Okay, all right, now suppose initially you had n constraints. Okay, so for the farmer problem, you had like 3 constraints. And in general, you could have lots of constraints. You can have n constraints. Okay. Then because the optimum is always defined by only 2 constraints, right? Because we're in 2D, so the optimum is only defined by 2 constraints, right? Then if you pick a random constraint out of these n constraints, there's only a 2 divided by n probability that it's one of these tight constraints, right? Yeah. And, so like here, right, we have 5 constraints. And so you only have a 2 in 5 probability of picking, if you pick a random constraint, there's only a 2 in 5 probability it's actually tight. Okay. And with a 3 in 5 probability, it's one of these useless constraints where if you remove that useless constraint, you don't actually change the optimum. Okay. Yeah. So if this constraint that you pick is not tight, then you can just throw it away and you don't change your optimum. Okay. So that basically gives us a way to simplify our problem. Okay. So the idea is that we're going to start with lots and lots of constraints, but there are only 2 useful ones. There are only 2 tight ones. And so, so then we're going to start throwing away all of these useless constraints, these redundant ones. Okay. And the way that you throw them away is, well, you just pick a random constraint. And with pretty high probability, it's actually useless. Okay. And so if you throw it away, you don't change your problem. However, you need a way to tell whether a constraint that you want to throw away is actually useless or it's actually one of these useful tight constraints. Okay, so you need because you cannot throw away any of these tight constraints, because if you do, then you change your problem. Okay, so therefore you need a way to distinguish whether the constraint that you picked is tight or redundant. Okay, so the way that you do this is, let's say that you pick any set of constraints G. Okay, so in total we have the set H of constraints, but let's say that G is a subset of H. Okay, right. Then we're going to let B of G be the optimum value for the C objective function subject to only these G constraints. Okay. All right, so now we have that if H in this big set of constraints, okay, if it's a redundant constraint, then we know that if you throw it away, you don't change the optimum. And so that means that the optimum, when you satisfy all of these, all the constraints in capital H, okay, versus the optimum when you satisfy all the constraints in big H minus this redundant constraint. Okay, these 2 optimums are the same. Okay, just like, for example, this is a redundant constraint, right? So if you throw this away, then the optimum after you throw this away versus before you throw it away are the same. Okay, so this gives you a way to check whether a constraint is redundant or tight. Okay, it's only it's redundant if and only if after you throw it away, you don't change your optimum. Okay. And also, if after you throw this away, you do not change your optimum, then what you know is that the optimum does not lie on this particular constraint. Okay, so for example, this constraint over here, right, we see that our optimum does not lie on that constraint. Okay, right. So now we basically have all the ideas we need to develop this algorithm. Okay, so now let's give the 2D LP algorithm. Okay. Right, so the algorithm is that if you only have 2 constraints, okay, then your optimum is just going to be at the intersection of these 2 constraints, okay, and then you're going to so this is going to be a recursive algorithm, okay. So the base case is where you only have 2 constraints, and in that case you just directly intersect these two half planes, okay, and their intersection is your optimum. Okay. And otherwise, you're going to pick a random constraint out of your constraint set. Okay. And then you're going to check whether this constraint is redundant or tight. Okay, and the way that you do that is you're going to find the optimum after you throw away this constraint. Okay? And the way that you find it is by recursion. Okay, so you're going to recursively run this 2D LP algorithm to find what is the optimum if you throw away this little h constraint. Okay, and what we said is that if the optimum if the optimum doesn't change after you throw away h, right? Then h is redundant. Okay, so if the optimum value does not violate h, okay, then the optimum value over here is equal to the optimum value for b of h. Okay, so what I mean by doesn't violate h is that, for example, suppose you chose to throw away this constraint. Okay, then the optimum actually satisfies this constraint that we picked, right? Because this constraint just says that we have to have the points have to lie on this side of this line. Okay, and this star point indeed lies to the side of this line. Okay, so this this optimum for b minus h, b of h minus little h, does not violate this h constraint over here. Oops. Okay, and in that case, we know that we know that this thing is equal to b of h. And so we can just, and since we've already computed this opt equals, equals this value over here, then we can just output the opt. Okay. Right. And otherwise, what happened is that so this is the case where h is redundant. Okay. But the other case is where h is actually tight. Okay. So if h is actually tight, then the optimum for after you take out little h versus before you take out little h is going to change. Okay, just like over here, right? Suppose you actually took out one of these tight constraints. Okay, if you took out one of these tight constraints, so if you chose this as your h, then your optimum would go over here, right? And you see that this optimum actually, if you take out this h, your optimum would be over here. Okay, oops. Okay, and you see that this point actually violates this constraint over here. Okay. All right, so then in that case, if you happen to pick one of these tight constraints, okay, then what you need to do is to take all of the other constraints, okay, big H minus little h, and then you're going to project them onto h's boundary. Okay, and then that's going to produce a 1D LP. All right, so I'll tell you more about this on the next page. Okay, what I mean by projection and forming a 1D LP. Okay, but anyways, just sort of so what we're going to do if we're in this else case is project all of these other constraints and then get a 1D LP, and then we're going to return the optimum of the 1D LP. Okay. All right, so what I mean by, okay, so now let's talk about what I mean by projecting the other constraints onto h's boundary. Okay, so what we need to do in this case, where if you pick this h, right, then you would have an optimum which violates this h. And then in that case, what you know is that the optimum actually has to lie on the boundary of h. Okay, so here you have h, and then you know that the optimum is going to lie on the boundary of h. Right, the boundary of h is this black line over here. Okay. And so therefore we have to find which line on this boundary is actually the optimum. Okay, and to do that, we're going to do this projection operation. Okay, so what is this projection operation? First of all, given a constraint, we're going to let this del of h here be the boundary. Okay, in other words, it's going to be the line which defines h. Okay. So all these black lines are boundaries. Okay, and now suppose you have a optimum which violates some constraint h. Okay, then we know that the optimum for b of h, okay, has to lie on the boundary. Right? The optimum has to be over here. Okay, and so what we're going to do is we're going to take all of these other constraints and we're going to project them onto h, onto the boundary of h. Okay. And in particular, for example, let's take this constraint and let's project it onto the boundary of h. Okay, so so this constraint, let's call this h prime here, right? Oops, Okay, H prime says all of the points have to lie on this side, right? And so if you, so by project, I mean that we're going to combine this H prime constraint with the H constraint, okay? And when you combine these two constraints, you see that you're going to cut off all of these points over here, which are allowed by H, but not allowed by H prime. Okay, so if you combine H prime and H, then we're going to cut off all of these top points. Okay, so now we've managed to project H prime, this constraint H prime, onto H. Okay, right, so now, so next we're going to project all of the other constraints onto H also. Okay, because we need to satisfy all of these other constraints as well as H. Okay, and so for example, which is, okay, so now let's pick this constraint. Okay, this is the next constraint we're going to try to satisfy. And this constraint says that everything has to lie on this side. Okay, and so therefore, you know, these points are allowed by H and the previous constraint we took out, but they are not allowed by this new constraint. And so when you project this new constraint, you're going to have to remove that little chunk. You see that we remove that little chunk that is not allowed. Okay, yeah, and so we just keep doing this for all of the remaining constraints. Okay, so if you do it, so if you do this for, if you now take out this constraint, you see that, you know, these points on H are not allowed when you project. Okay, so we're going to be left with these points. And then if you add the final constraint, we need to take out this little top part over here. Okay. All right, so then after you do all of these projections, you see that what you're left with is this 1D LP. Okay, so in fact, we no longer have this purple region here. We just, because what we know is that the optimum actually has to lie exactly on this black line, right? So if you go back to initially, what we have as that the optimum should actually be over here, right? Once you add in the H, then this is not feasible anymore. So the optimum is actually over here. And this point lies exactly on the boundary of H. Okay, yeah, so after we do all of these projections, we see that the optimum has to lie exactly on the boundary of H. And the boundary of H is just a line, so it's just a 1D region. Okay, so previously we had a 2D LP, right? So previously our feasible region was two-dimensional, but now after all of these projections onto the boundary of H, we end up with a 1D LP. Okay, so if we go back to the previous algorithm, right, this is why we said that after you do all of these projection operations, you're going to end up with a 1D LP. Okay. And then the final step of the algorithm is to output the optimum of the 1D LP. Okay, and so we want to output the optimum of this 1D LP on this line over here. And this is actually very easy because, you know, since we're trying to move up as much as possible, then the optimum is just, so on this line, we're trying to pick which point is as high as possible, right? So that's just the top point on this line. Okay, so the optimum is just going to be right over here, right over here. Okay, if we were trying to move in this direction, right, then the optimum would be over here. Okay, but in any case, whichever direction you're trying to move, it's going to be at one of these two endpoints of the, so for example, if you're trying to move in this direction, okay, then the optimum would still be at this top point over here. So the optimum for this 1D LP is going to be at one of the two endpoints of this line segment that you end up with. Okay, so are there any questions about this 2D LP algorithm? Okay, so let's go back to the algorithm. Okay, so again, the algorithm is that we're going to, if you have lots of constraints, you're going to pick a random constraint. Okay, and hopefully this is a redundant constraint. And the way that you figure out whether it's redundant or not is you compute the optimum after you take out this constraint. And if the optimum doesn't change, okay, so that's the first case, the optimum does not violate H, then the optimum for these constraints is equal to the optimum for the H constraints. And so we're done. Okay, and otherwise, the constraint that you picked, the constraint that we picked was tight. And so that means that the optimum actually lies on the boundary of H. Okay, otherwise the optimum lies on the boundary of H. And so we're going to project all of these other constraints onto H's boundary, and that's going to produce a 1D LP. Okay, it's basically a line segment. And then you're just going to output the optimum for that 1D LP, which is always going to be one of the endpoints. Okay, any questions about this? Okay, yeah, if you have questions, you can also ask later. All right, so next we're going to look at, we're going to analyze this algorithm and see what its time complexity is. Okay, so because this is a randomized algorithm, we're going to analyze the expected time complexity. Okay, so let's let T of n be the expected time to solve a 2D LP where you have n constraints. Okay, all right, and the claim is that T of n is going to satisfy this equation over here. Okay. So let me explain what all the terms in this equation are. Okay, now first of all, this T of n minus 1 term. Okay, this is because the first thing that you do in the algorithm, in the previous algorithm, was that you need to go recursively find the optimum of this h minus little h. Okay, so there are m minus 1 constraints over here, and so to do that recursion is going to take you t of n minus 1 time. Okay, so that's the first term. Okay. And then next, you need to check whether the optimum that you get from the recursive solution violates the constraint that you took out, this little h. Okay, so that's going to take constant time because you just need to take this. So this is going to produce a point over here, right? This recursive solution is going to be some point, and you just need to check which side of h it's on. Okay, so that's like a dot product. So that would take constant time. Right. Now there is a there's only a 2 in n probability that the constraint little h violates the optimum. Okay. So if it doesn't violate the optimum, then the algorithm terminates. Okay. But there's a 2 in n probability that it does violate little h, the optimum violates little h, in which case we have to do all of these projection operations. Okay. So each of these projections, so we're taking each of these constraints from h minus little h, and you're projecting onto the boundary, right? So each of these projections takes constant time because it's just taking a line and then projecting it onto some other line segment. Okay, so that takes constant time. And since you have m minus 1 constraints over here, then altogether it's going to take you order n time to do all the projections. And then after you do all the projections, you're going to end up with a 1D LP. Okay. And then you have to solve that 1D LP, but as we said, the solution is always going to be one of the endpoints. Okay, so then you just need to check both endpoints, and that takes you constant time. Okay, so altogether, we have this expression for T of n. Okay, and if you solve this expression, you're going to get that T of n solves to linear time. Okay. So therefore, we have a linear time algorithm to solve a 2D LP with n constraints. Okay. Any questions? Okay, now there are a few, so the algorithm we gave doesn't work in all cases. Okay, so there are these like very special corner cases where the algorithm will actually, the previous algorithm will actually fail. Okay. However, these corner cases are, first of all, they're unlikely to occur in practice. Okay, and second of all, we can have other algorithms to deal with all of these corner cases. Okay, all right, but let me tell you what these corner cases are. Okay, so the first corner case is that you could have an LP which is completely infeasible, and what that means is that there are no points which satisfy all the constraints. Right. So for example, suppose you have constraints that you have a variable x1 is larger than 1, and you have another constraint where x1 has to be less than 0. Okay, well, those are infeasible. You cannot satisfy both constraints at the same time, and so therefore this LP doesn't have any solution. Okay, another example would be something like this. Okay, so here we're saying that you want points which lie on, which lie to the, on these sides, and there are no points like that. So therefore, this is infeasible. Okay. All right. Okay, so that's the first corner case. The next corner case is you could have a LP where the optimum is actually infinite. Okay, so suppose you're trying to maximize a function, right? And suppose your feasible region looks like this. Okay, looks like this yellow region over here. Okay, then if you're trying to sort of move up as far as possible for your optimum, okay, then you see that you can move infinitely far. Okay, so therefore this LP has an unbounded maximum. Okay, and the final corner case is, so previously we said that the optimum always lies at the intersection, at a corner point where two lines intersect. Okay, but it is possible that the optimum does not lie at an intersection. So for example, in this case, if we're trying to go as up as possible, then if you have a constraint which is just this horizontal line over here, okay, then all of the points on this upper line segment, all of them are optimum points. Okay, so you could have a non-unique optimum. Okay, right. So yeah, so we have these special cases. However, it's possible to take any LP and then pre-process the LP to check whether you have any of these special cases. Okay, and if you have a special case, we're going to use another algorithm to take care of these. Okay, these corner cases are actually pretty easy to take care of once you have a general LP algorithm which can take care of the non-corner cases. Okay, right. So that's why we, in general, we're going to ignore these corner cases. Okay, because first of all, they're unlikely to occur, and even if they do occur, we can tell when they occur. Right, we can check for them, and then we can still use our standard LP algorithm to deal with these special cases. Okay, right. So next, we're going to move on to higher dimensions. Okay, so previously we talked about this two-dimensional LP. Okay, but in general, you could have higher dimensional LPs. So, for example, previously we had a dimension for wheat and barley, right? But you can imagine, this farmer wants to plant more things, like maybe rice and then I don't know, like millet and a bunch of other things. Okay, so yeah, so the number of variables that you have in your LP, that's going to be the dimension of your LP. And when you have higher dimension LPs, then whereas previously we had constraints which were represented by lines. Okay, when you move to higher dimensions, the lines are going to change into hyperplanes. Okay, and the set of points which satisfy these hyperplanes is going to be a half space. Okay, so as a picture of this, so for example, so here you could have like maybe a half space like that. Okay, so we're trying to consider all the points which are in this little sort of pyramid shape in the center, right? So maybe you have a half space where this half space says we only consider points which are to the left of the side. Okay, and then you have another half space which is like like this slanted thing over here, and then we have to be sort of below this point. Okay, so you can see that this figure over here can be obtained by intersecting a bunch of half spaces. Okay. And so the intersection of all of these half spaces is going to be the feasible region when we're in higher dimensions. Okay. All right. Now, a key property about these intersections is that the feasible region, right, this intersection is going to be convex. Okay, so that's not hard to prove, but basically, anytime you add a new half plane, right, you're going to intersect it with the previous feasible region, which is already convex. And so when you intersect it with a half plane, a half space, then that's going to form a new convex region. Okay. Right. So our feasible regions are going to be convex, and we're going to call those regions polytopes. Okay. And now, just like in the 2D case, where the optimum value was at a corner of our 2D polytope, right? So previously we had this, sort of 2D polytope, and our optimum was at one of these corners. Okay. Likewise, when you move to higher dimensions, the optimum point is going to be at one of the corners of this polytope. Okay, and the corners of the polytope are determined by the intersection of d half spaces. Okay, so in 2 dimensions, they're determined by the intersection of 2 lines or two half planes. Okay, and in d dimensions, they're determined by the intersection of d half spaces, which correspond to d constraints. Okay, and the objective function also defines a direction that we're trying to move in. Okay, so for example, this might be the direction that we're trying to move in. And so what we're going to do is we're going to take all of the planes which are perpendicular to this direction, and we're going to move them as far as possible in this direction C, while still intersecting this polytope, this little region over here. Okay, right. And then you can see that you can move you can move a plane in this direction C as far as So after you're just about to leave the polytope, right, then you're going to hit exactly one of these corner points, right? So that's why the extreme is always at a corner point. Okay. So the optimum is always going to lie. So because it's going to be at one of these corner points, then the optimum is always going to be at the intersection of D half spaces, right? Right. Now, in general, the number of corner points that you can have on this polytope can be exponential. Okay, so you could have a very complicated looking polytope. Okay, so for example, if you imagine a hypercube, right? So if you imagine like a 2D cube, right? So you can form this by just having 6 constraints, right? There's 6 sides. Okay. However, there are 2 to the 3 number of corner points on here. Okay. So in general, in D dimensions, right, you can have draw a hypercube using 2 times D number of constraints, but you will have 2 to the D power number of corner points. Okay, and any one of these corner points could potentially be your optimum. So therefore, polytopes in higher dimensions can be very complicated. Okay. However, we can still use the basic idea for the 2D algorithm and use it to solve D-dimensional LPs. Okay, so here's the algorithm. Okay. Now, this algorithm actually looks very similar to the previous 2D algorithm. Okay, so if you go back and you compare these two things, you can see that they're very similar. Okay, and the basic idea is, almost exactly the same. Again, what we're going to do is to pick a random constraint. Okay, and in this case, we have since we know that the optimum is going to lie at the intersection of D half spaces, then if you have n constraints in total, then the probability that you pick a tight constraint. Okay, a tight constraint is a constraint which is one of these D constraints at the optimum. Okay, so the probability that you pick one of these tight constraints is going to be D divided by n. Okay, and if you so if you happen to pick a non-tight constraint, a redundant constraint, okay, then you can just throw that away. And if you picked a tight constraint, then you know that the optimum is going to lie on this tight constraint, and then you're going to project all of the other constraints onto this tight constraint. Okay, so this is just like the 2D algorithm. Okay, right. So more precisely, we're going to pick this random constraint H. Okay, and then you're going to recursively find the optimal solution if you take out this H constraint. Okay, and if you take it out, and the optimum over here is equal, if it does not violate the constraint that you picked, okay, then that would mean that after you take out the constraint versus before, you have the same optimum. Okay, and so in that case, this optimum over here is exactly your solution. So you just output that optimum. Okay. Otherwise, this H that you picked is actually a tight constraint. And if it's a tight constraint, then you know that the optimum actually lies on H. And so in that case, you're going to take all of the other constraints and then project them onto H's boundary. Okay, sorry, it doesn't just lie on H, it lies on H's boundary. Okay, so you're going to take all these other constraints and project them onto H's boundary. And when you do that, you're going to end up with a D-1 dimensional LP. Okay. Yeah, so again, the projection operation just means that here we have these half spaces, right? And D's boundary is a D-1 dimensional space, right? So like in 2D, in 2 dimensions, H's boundary would be a one-dimensional line segment, okay? One-dimensional line, okay? And in general, in D dimensions, then H's boundary is going to have D-1 dimensions. Okay? So you're going to take each of these half spaces and intersect it with this d-1 dimensional boundary of H. Okay, you're going to do that for all of the constraints in capital H minus little h. Okay, and so that's going to end up constraining you to this d-1 dimensional boundary of H. Okay, and so now this is going to be a d-1 dimensional LP lying on H's boundary. Okay, and then now we're going to do a second recursive call to solve this d-1 dimensional LP. Okay, so that's the algorithm. Any questions about this? Okay, all right, so then now let's look at the time complexity for this algorithm. Okay. So, this analysis is, or this complexity is going to be a function of two variables. The number of constraints that we have, which is n, and the dimensions that we're working with. Okay. And the claim is that this time complexity is going to satisfy this equation, or this inequality, this expression. Okay. All right, so let me show you what all these terms are. Okay, so the first term, this one over here, right? This is because you need to recursively find the optimum after you take out one constraint. Okay, so if you take out one constraint, then you have n-1 constraints, and you're still in d dimensions. Okay, so that's the first thing you need to do. And then after that, you need to check whether this optimum is going to violate the constraint that you took out. Okay, and so that's, again, going to involve some sort of dot product, but because we're in d dimensions now, this is going to take order d time. Okay, right. Now there's a d divided by m probability that we actually picked a tight constraint. Okay, and in that case, the optimum is going to violate h, the constraint. Okay, yeah, and again, the reason is because the optimum lies at the intersection of d constraints. So if you pick a random constraint h, right, then there's a d divided by m probability that it is one of these tight constraints. In which case, once you take it out, you're going to violate h. Okay, yeah. So, okay, so that's where this d divided by n comes from. Okay. All right, now, if you violate h, right, then you have to take all the other constraints and project them onto the boundary of h. Okay, so there are m-1 constraints over here, right, and to project each of them onto the boundary of h, that takes order d time, because we're in d dimensions. Okay. So therefore, all the projections together take you order dn time. Okay, and then after you do all these projections, right, then we're down to a d-1 dimensional LP, okay, because the boundary of h is d-1 dimensional. Okay. And furthermore, yeah, so we're down to a d-1 dimensional LP, and we also took out one of the constraints, so we're down to n-1 constraints. And then we have to go solve that that new d-1 dimensional LP, right? And this is going to take this much time. Okay, so that's where we get this term over here. Okay, yeah. So that's how you get all the terms in this expression. And now, if you solve this, so I'm not going to do this manually, but it turns out that if you solve this expression over here, you're going to get that the time complexity is going to be order of d factorial times n. Okay. All right, so this time complexity is still linear in the number of constraints. Okay, so like in the 2D case, it was just order n. Okay, so it's linear in the number of constraints, even in the d-dimensional case. Okay. However, it's exponential in the number of dimensions. Okay, so the more variables you have, then this complexity is exponential in that, in the number of variables that you have. Okay, so that is the randomized LP algorithm. Are there any questions about this? Okay, so then yeah, so then I just want to say a few more things about linear programming before we move on to something else. Okay, so first of all, the way that we formulated our problem was that we wrote down these inequalities. Okay. So you can do this a bit more systematically using matrix notation. Okay, so for example, the objective function over here, right? So if you write this using matrix notation, you can write it as a dot product of two vectors. Okay, where the so here you put all the variables that you have, right? So in general, if you're in d dimensions, then you're going to have a d-dimensional vector representing all of your variables. Okay, yeah, and all of the constraints can also be written in matrix format, like we have over here. Okay, so in general, if you have let's say all right, so let's say that you're in n dimensions, okay? Then the objective can be expressed as a dot product of two size n vectors, right? And the constraints can be expressed as the product of a m by m matrix, which expresses all the constraints times the vector containing all of the variables, okay? And the constraint values are given by this b vector over here. Yeah, so in general, you can use this systematic matrix notation to talk about things. Okay, so next, so we looked at one algorithm for LP, right? But there are actually many algorithms to solve LPs because it's such an important problem. Okay, so one of the first LP algorithms, which came out many years ago, like way back in like the 40s. Okay, so this was when people first started looking at LPs. And so Danzig proposed this very famous algorithm called the simplex algorithm. Okay. And so the simplex algorithm is, so it's, again, it's based on this observation that the optimum lies at a corner of the polytope that we're trying to optimize. Okay, so here, if you have some sort of polytope given by your constraints, then we know that the optimum lies at a corner point, which is the farthest point in this direction C that we're trying to go. Okay. And so the simplex algorithm is basically, it's something like gradient descent. Okay, so what it's going to do is it's going to walk along the boundary of this polytope. Okay, and it's always going to walk in the direction of C. So for example, suppose you start over here. Okay, so it's some sort of iterative algorithm where we're going to move to different points, and these points are going to keep improving the objective function, objective value, until you cannot improve it anymore, and then you stop the algorithm. Okay, so suppose initially you're at this red point over here, right? Then we want to move as far as possible in this direction C, and so let's say that you move in this direction. Okay, now once you're at this point, you're again going to move in the direction C, but you have to stay on the face of this polytope. Okay, and you have to move to one of these corner points. Okay, so for example, you're not allowed to move in that direction. Okay. Right. So then we're going to move along one of either this way or that way. And in this case, we're going to move up, right? And then we're just going to keep moving until eventually you get to a point where at this point, you can no longer move in the direction C. Okay, because if you move in any of these directions, you're actually going to move against the direction C. Okay. Yeah. So this point is basically it's a local optimum, but because we're working with linear programs, the local optimum is also a global optimum. Okay, so it's kind of like like gradient descent or gradient ascent in this case, because we're trying to maximize, right? Where you're always moving as far as possible towards in the direction of your objective. Okay, yeah. So that's the simplex algorithm, and it turns out that in the worst case, the simplex algorithm can actually be exponential time. Okay. However, in practice, when you run the simplex algorithm, it's almost always very fast. Okay, and it's also very easy to implement, and so that's why this is this algorithm is widely used in practice. Okay, even though it's a very old algorithm, and in the worst case, it can be exponential time. In practice, it works very well, and so this is widely used. Okay, but people wanted to have a guarantee that you could you have an algorithm which can always run in polynomial time. Okay, and so the first polynomial time algorithm for LP was an algorithm called the ellipsoid algorithm by Khachiyan in 1979. Okay, and yeah, so I'm not going to describe how this algorithm works, but basically what you do is you so instead of looking for the optimum point in a polytope, so in this case our polytope is this blue region over here. Okay, so instead of looking for the optimum point in the ellipsoid algorithm, all you're trying to do is you're trying to find one point which is in this blue region over here. Okay. So it turns out that as soon as you can find a point which is in this blue feasible region, then this is actually equivalent to finding the optimum, because you can do some sort of transformations to transform this single point which is in the blue region, right? So suppose you found this point, right? You can somehow use this as a subroutine in order to find the optimum. Okay, so the goal for the ellipsoid algorithm is just to find any point which is in this feasible region. Okay, and the way they do that is they create a sequence of these ellipses. Okay, so the first one is this red ellipse, and the second one is this green ellipse, or a green circle actually. Okay, but in general they're going to be ellipses, okay, or higher dimensional ellipsoids. Okay, and the property about these ellipsoids is that they're always going to contain the feasible region. Okay, you see the blue region is in both the red ellipsoid and the green ellipsoid. Okay, and furthermore, as you go along this process, the ellipsoids are going to shrink in size. Okay, yeah, and so eventually you're gonna get down to like a very small ellipse, right? Ellipsoid, which is actually going to lie within your feasible region. Okay, and in that case, you found a point which is in your feasible region. Okay, yeah, so you keep finding a sequence of these ellipses which get smaller and smaller, and which always enclose your feasible region. And at the end of this process, you're going to get something. You're going to find a point which is inside your feasible region. Okay, and then the volumes of these ellipsoids actually decreases exponentially. And so you can use this to show that this algorithm will find a feasible point in polynomial time. So it will solve LP in polynomial time. However, in practice, this algorithm is actually quite slow. Okay, even though it is polynomial, it's in practice it's rather slow. And so this is mostly interesting because it was the first theoretically provable algorithm which was polynomial time. However, in practice, there are also practical polynomial time algorithms for LP. Okay, so these are these interior point methods, which was first proposed by Carmarker. Okay, yeah, so these algorithms are actually very fast in practice. Okay. And they differ from the simplex algorithm because the simplex algorithm always tries to stay on the boundary of the polytope. Okay. Whereas the interior point method, as the name kind of implies, it's going to move within the interior of the polytope. Okay. And from this interior, it's going to follow some sort of path, and eventually it's going to end up at one of the corners of the polytope, which is the optimum. Okay, all right, so so I'm not going to have time to talk about these in more detail, but you can look online for sort of pretty reasonably understandable explanations about both the ellipsoid algorithm and the interior point methods. Okay, so the interior point methods are actually used a lot, not just for LP, but for also other types of optimization problems. Okay, now I just want to mention a few applications of LP, right? Because I said that you can use it in many, many places, and in fact, it's one of these very, very important algorithms. Okay, so in fact, it was so important that when the first polynomial time LP algorithm was discovered, right, it actually made it into the New York Times. Okay, and not only that, the inventor of the algorithm was actually from the Soviet Union. Okay, and this was back in the 1970s, but the New York Times still sort of thought it was worthwhile to talk about this Soviet computer scientist who discovered this polynomial time LP algorithm. Okay, so one application of LP is for network flow. Okay, so we talked about network flow, and we saw that you have a bunch of different algorithms to solve network flow problems. But actually, you can formulate network flow as a special case of linear programming. Okay, so you can create a linear program which models network flow. Okay, and the way that you do this is, so for example, in network flow, what we're trying to do is to maximize the amount of flow which comes out of a source node. Okay, so then what you do is we're going to create these variables f of sv. Okay, so this is not a function here. This is just a variable. Okay, f of sv is just going to be a number. Okay, and it's going to represent the amount of flow from the source node to some other node V. Okay, and in network flow or in max flow, what we're trying to do is to maximize the amount of flow coming out of the source node to any other node. Okay, so therefore you want to maximize the sum of f of SV from S to all of these other nodes. Okay, and again, each one of these things is just a number here, right? This is just a number. Okay. Right. However, we have these constraints that we need to satisfy. Okay. So first of all, we have the right. I guess I wrote all these constraints. Okay. So we have the capacity constraint, which is that the amount of flow from a node U to V. Right. This is this can be no more than some capacity constraint from U to V. Right. And we have this symmetry constraint, which is that the flow from U to V is opposite of the flow from V to U. And then we finally we have this conservation constraint, which is that the amount of flow which goes into any node other than the source or the sink node, right? The total amount of flow has to be 0. Okay, so if you have like lots of incoming flow, right, then you then the outgoing flow has to equal the amount of incoming flow. Okay, so if you have like 10 going in, then you could have like 3 and 7 going out. Okay, and the way that you express this is that you just take any node, right, and you say that if you look at the flow from this node V to all of the other nodes and you add them together, then this has to be 0. Okay, because here if the flow goes in this direction, if it's 3, then the flow coming into V is actually -3, right? And here the flow, and if this is like 7 over here, then the flow going into V is actually -7. Okay, so if you add up 10, -3, and -7, then you get 0, and this has to be true at every node. Okay, yeah, and so this means that you can express all of the constraints in network flow using linear constraints. Okay, and the objective is also a linear objective, and so therefore this is a linear program. You can model the whole thing using a linear program. Okay, so you can use linear programming algorithms to solve network flow. Okay. However, even though you can do this, it doesn't mean that in practice you want to do this. Okay, because in general, linear programming algorithms, even though they're polynomial time, they're still going to be slower than the network flow algorithms that we have. Okay, because network flow is kind of like a very special type of LP. So we have like very special algorithms which are optimized for the network flow problem. Okay, as opposed to these general LP algorithms. Okay, yeah. But at least it's possible to express network flow and many other types of flow and scheduling and many other types of problems. You can express them using LP. Okay, so are there any questions about LP? How to calculate. All right, so you just exactly run recursively run the algorithm. Okay, oops, let me go back a bit more to the previous slide. Yeah, right. So this is an algorithm to calculate, if you have n constraints and d dimensions, right? So this is an algorithm to find the solution. Okay. Now in this step, you just run this algorithm recursively, except for you take out one of these constraints. Okay, you're still in d dimensions, but you take out one of the constraints, and so you just run the algorithm recursively. Right. After you run this algorithm recursively, you're going to get a value, right? The output of this algorithm is just some sort of optimum value. Okay, and you just compare. It's going to be an opt. This opt is actually a point. Okay, so this is some particular point, which is this optimal point over here. Okay, so imagine that your algorithm outputs this point for you. Okay, and now you're going to take this point, and you're going to see whether this point violates the constraint that you took out. Okay, so if your constraint is like, everything on this side and your optimum point is over here, then it violates that constraint. Okay, but if the optimum is over here, then it does not violate that constraint. Okay, yeah, and if it violates the constraint, then you know that this h is actually, if we're in the first case over here, then we know that this h is actually a tight constraint, and the actual optimum, when you want to satisfy all these h constraints, has to be somewhere on h. Okay, on this little h. And so that's why you're going to project all of these other constraints onto h's boundary. Does that make sense? Can you show how to do projection? Yeah, sure. So the projection basically, yeah, so the projection is, so suppose we know that the optimum lies on some constraint, little h over here, okay? Actually, we know that it lies on the boundary, okay? So we know that it lies on this line over here, okay? So the projection just means that you take all of these other constraints, which are h minus h, and we know we need to satisfy all of these other constraints in addition to h. Okay, so suppose you want to satisfy this constraint, okay, then you need to be on this side, right? Furthermore, you need to satisfy the h constraint, so you need to be over here, okay? So if you add together these two constraints, then you see that, then you see that we're going to chop off this little region over here, okay? So that's how you do the projection in 2 dimensions. Okay, and in higher dimensions, each of these h constraints is going to be a d-dimensional hyperplane. Okay, d-dimensional hyperplane. Okay, and then you need to project that d-dimensional hyperplane onto the boundary of h, which is now going to be a d-1 dimensional. So the boundary of h is going to be a d-1 dimensional hyperplane. Okay, yeah. So, exactly the math for that, I'm not showing the exact math for that, but, in general, you're just trying to intersect one of these d-dimensional hyperplanes with a d-1 dimensional hyperplane. Okay, any other questions? Why does it not check tight constraint h from the bottom up? Oh, okay. Yeah, I don't know. It's possible to like redo this algorithm to do what you're saying, but yeah, the way the algorithm is currently formulated is that, and it's a very nice formulation, right? It's a very nice recursive formulation, but the current formulation is just that you see what happens if you take out this little h constraint, okay? And if nothing bad happens, right? If you don't get the violation, then you know that the thing that you calculated over here is already the optimum, right? So for example, let's go back to this. I have to go back very far. Yeah, right. So yeah, so if you took out, like this guy over here, right, and then when you calculate the optimum without this constraint, okay, well, the optimum is still going to be over here, and because this optimum does not violate this constraint, right, then you know that this optimum is the correct optimum, and so you can just go ahead and output that optimum. Okay, but if you happen to pick like this constraint, right, then your optimum would move over here, and now this optimum actually does violate this constraint, and so now you know that you picked one of these tight constraints, and then now you're going to have to like do the optimization on this boundary over here. Okay, so that's just how they set up the algorithm, and it's a very nice recursive formulation. So it might be possible to somehow reformulate this to do what you're saying. Okay. Okay, any other questions? Okay, well, yeah, so I was supposed to start a new topic today. In fact, we're supposed to start a new section of the course about approximation algorithms. So I guess I don't have time to cover much of this. Let me just get started by going through the first, let's say, 2 slides. Okay, so they're very simple. They just introduce the concept of approximation algorithms. Okay, and next time we're actually going to see one of these approximation algorithms. Okay, so so the idea is that for the algorithms that we looked at up to now, basically all of them have always found the optimal answer. Okay, for example, this LP algorithm, right? It finds you the optimal answer. Okay. However, we know that there are lots of problems where there's no efficient algorithm to find the optimal answer, right? Unless p equals np, which is unlikely. Okay, so we don't know of any efficient algorithms for many of these problems that we need to deal with. Okay, and many of these problems are actually very important in practice. Okay, however, we do not have efficient algorithms for these problems. Okay. So the question is, what do you do? Okay, you have this important problem that you need to solve, but you don't have an efficient algorithm. Okay. Well, one thing that we talked about is that maybe you can consider special cases of this problem. And the special cases might be easier to solve than the general case. Okay, so we talked about some of those algorithms in a previous lecture. Okay. But another thing that you can do is that if you cannot get the optimal answer, you can just try to get a good enough answer. Okay, let's try to get a pretty good answer as opposed to the optimal answer. Okay. And so, so this is what approximation algorithms try to do. Okay, they try to find an approximately optimal answer, not necessarily the best answer. All right, now let me just introduce some terminology for approximation algorithms, which is this approximation ratio. Okay, yeah, so just give me 1 minute and I'll talk about the approximation ratio and then we'll finish next time. Okay, so suppose you have a, let's say a maximization problem X. Okay, so you're trying to maximize some value. Okay, and let's say that you have an algorithm A to solve X. And now let alpha be any constant larger than 1. Okay, then we're going to say that A is an alpha approximation algorithm for the problem X. If A always outputs an answer which is at least 1 divided by alpha times the optimal. Okay, so it doesn't get you all the so we're trying to make the solution be as large as possible. Okay, and here I might only give you a solution which is like 80% of the optimum, okay, or 50% of the optimum. Okay, yeah. So whatever and we want alpha to be small. Okay, so the smaller alpha is, the better the answer I'm providing. Okay? So for example, if X here is the problem of max flow, right? Then if you have a 2 approximation algorithm for max flow, then that means that you output a flow which is at least half as large as the maximum flow. Okay. All right, so those are for, yeah, and the smaller alpha is, the better the approximation. Okay. All right, and now if you have the opposite where you have a minimization problem, so you want to make X as little as possible, right? Then you can still talk about an alpha approximation algorithm. And now you're going to get, this algorithm is going to return an answer which is at most alpha times larger than your optimal. Okay, so for example, if you're talking about min cut, right? So we're trying to find a very small cut here. Then in this case, if you have a 2 approximation algorithm, it's going to find you a cut, and this cut is only 2 times, at most 2 times as large as the smallest cut. Okay. Right. And again, for minimization problems, you also want alpha to be small. Okay, so if alpha is like 1.1, right, then when you then we're going to get then this min cut algorithm. If it's a 1.1 approximation, it will return a cut which is at most 10% larger than the optimal. Okay, so yeah, so in general, we're not going to look for the optimal solution anymore. We're going to look for an alpha approximation where alpha is as small as possible. Okay. All right, yeah, so next time we'll talk about this problem of set covering, and we'll see how to design an so this is an NP-complete problem, but we'll see that we can design a, a good approximation algorithm for this problem. Okay, all right, any questions?